what we're doing, stop what we're doing, close Chromebooks. We're gonna talk about next time. Talk about what the unit is, the new one. So we're moving on to 5.1 and 5.2. We combine them, okay, because they're energies, and it doesn't do a whole lot if we just talk about one at a time. So we're gonna combine them, do them all together. So, next time you come, we're gonna be doing a lab with this little setup right here, okay? We're gonna be shooting stuff up into the air, measuring the energies, okay? So, we need to talk about energy, that kind of thing to start with. So, first thing we want to show you is what we call an LOL diagram, okay? Okay. So, we use it to track energy to help us to see what's going on. So, what we want to do is, first of all, we want to think about when I compress this spring, what have I done to the spring? How did I give energy to the spring? What did I do? Physics terms. No, what did I do? Oh, okay, we're good. Yes,
Sorry, I'm just.
it can see you, yes.
That's all. Yeah.
What did I do on it in terms of physics to get energy into the spring? A force, and I made it move a distance, so I did work. I did work on the spring, right? When I do work, when you do work, you're either putting in or taking out energy. That's what we're doing. When we do work, we transfer energy. So I do work on this spring, and it gives that spring energy. So that spring stores energy, right? And when I release it, where does that energy go?
Into the little.
Into all the objects, right?
Yep.
Okay. So what kinds of energy do we have in this? We have kinetic energy. You said potential. There are some kinds of potential. What kinds of potential do we have?
Spring.
We have a spring, because when I compress or stretch a spring, I put energy into it, right? Or we can if we use some other machine. So there's a spring potential. What other kind of potential?
There's also the potential of the like tape and little wooden thing.
Potential, what do you mean?
Because like when you put them, there's potential when it's sitting up there at the top, right? Because it wants
Because
it wants to go down.
it wants to go down, so there's some, so what kind of potential energy is that? So that's gravitational potential energy.
Matt, don't you have potential energy?
How so?
Because right now your arms are doing nothing, but they have the potential to put
What are you saying about my arms?
nothing. I'm
That
saying.
they're just like, there's nothing there?
No.
Just
Wow, that was
insulting
kind
me
of
again.
offensive.
That's just, you guys call me short, now you're calling me weak.
Potential energy
Okay,
is like.
so you're saying
sitting on
that they're not doing anything,
right now,
okay?
but if you want, you could go over and press down.
How do I do that?
You would use chemical
What?
energy.
There you go.
Use
So that
it
would be
to
a
a higher
chemical
state
potential energy.
Right.
to get-
But what we're gonna do is we're gonna really limit our system to this right here, okay?
Yeah.
So that, in our LOL diagram, let's go back to that, the circle in the middle, that's where we put, what is our system? So for this one, we're gonna look at our energy. It's the tape. It is the plate. Spring. And the stand. So outside of that, we're not gonna worry about it. Because we could make the system that and me, we can make it the whole world, we can make it the whole universe, that gets kind of complex. So we're just gonna look at this. But you are right, if we include me, I would have chemical energy inside of me. That's what allows me to do the work on the spring. Yeah. Right. So back to this one, what other types of energy do we have in this? In our system, let's limit it to the system that we've got here. So what other types of energy do we have?
I mean, technically, wouldn't you have thermal energy?
Where?
The springs rubbing on the stand.
Yeah, that's pretty.
And the plate and the.
Okay, so you're saying from the friction, we're having thermal. So let's do this. How much do we really have?
Not rubbing.
Okay, and thermal energy, what kind of energy is it?
Kinetic.
It's actually kinetic energy, isn't it? Because that's the motion of the molecules, right? So really, that'll be tied up in our kinetic energy. Okay? But we could count maybe that we might have some types of kinetic, because if we were talking about a thermal kinetic energy, we don't want that, do we? What we're really trying to do, we're just trying to shoot this thing, right? That's what would be fun, to be able to have a war, we could go shoot it around, right? That's what we want. We want this to fly off. Any other kinds of energy, kind of like waste energy. So we could say that kinetic thermal is a waste. It's where we're going to lose some energy. Okay? What other? Any other types of energy? No?
$5.
Are forces energy?
Our force is energy. Tell me that.
No.
No, because energy is the potential to do it.
Okay. And force is measured in? Newtons. Energy is measured in? Work is measured in? Joules. And isn't work a force over a distance?
Yes.
So they're related, but they're not the same thing.
So if there's like the springs pushing up on the thing.
On the
would that-
plate? Okay.
Yeah, would that be a convert to like some sort of energy?
Well, isn't that what, so what happens is, I do work on the spring, it smashes the spring, right? We store that energy. Now, when I release it, there's a force applied over a distance, isn't there? So the work the spring does transfers the energy from the spring to the plate and the tape, right? So again, work is transferring that energy. So we get a force that applies over distance, that's the work. That's how we transfer that energy to the tape.
So is that the one we already have up there then?
Is that, what do you mean that?
You have the energy, the potential energy of the spring, is that what you were just talking about?
Well, all I was saying was that I transferred the potential from the spring to this by doing work. So we have that energy listed because we have the spring potential, but I was saying that that's how we just change the energy from one to another. Okay? Because that's the rule, isn't it? What's the rule with energy?
Can't be destroyed.
Yeah.
Can't be destroyed or
Created.
created, only,
So it doesn't
Change.
cycle.
and it's not just energy, it's energy and mass. So energy and mass can neither be created nor destroyed, only changed. What's that called? The law of conservation of matter and energy. So there's always a price. We can't just get rid of stuff. Okay? We have stuff, we can change it, we can manipulate it, we can put it somewhere else, but it's always going to be there. Okay? Make sense? So far? So are there any other types of energy in this system?
I don't think-
Huh?
Maybe like the spring pushing against the stand, but
Well, but is that a different type of energy?
no.
No. So we've listed all of our, okay? So when we go back to our LOL diagram, that's what we're going to put on. These are going to be bar graphs representing our energy. Let me extend that a little bit. So we're going to list them. We have a potential spring energy. We have a potential gravitational energy. We have a kinetic energy. Now I'm going to add one other category. It's not really a type. I'm going to put lost energy. Because we're going to say that anything is lost that doesn't go to make this tape go into the air. Okay? So if it goes somewhere else than into the tape, we're going to call it lost energy. Okay? And then we include the total energy. And this first graph is what we would say is for before, okay, or state one. This one is for after or state two, and we list the same energy. So we have the potential spring, the potential gravitation, the kinetic, the loss, and the total. Okay. And so what we're going to do is we're just going to sketch a bar graph that shows how much energy is in each one of those. Okay? Yeah. Tell me what I can go on. Yeah.
So it's the before when the spring is like compressed to the very bottom.
Before is wherever we say it is.
So I'm after
Okay.
when it's compressed.
So what we're going to do is we're going to say before is right here.
Yeah,
After is when the tape is at its very highest.
Okay.
That's what we're gonna do, right? So we're gonna say before is, so I just put spring compressed,
But you know, why do we have two?
and then tape in the air. Why do we have two what?
Why do we have two different graphs again?
This is for the state, the beginning state. This is for the ending state.
But wouldn't each state just be a point and not a line?
We're not making our-
Where the line represents how much energy.
Oh yeah, this isn't a line, this is a bar graph.
There's a, well, line or, so when I say line, you're talking about a line like this, right?
Yeah. But
Yes, no, it's going to be a bar graph. So let's look at it. Let's go ahead, let's get rid of that one. Let's go ahead and do that. So let's say state one, our before state, is with the spring all the way compressed. We're just holding it right here. So tell me about each one of these energies. How much potential spring energy do we have?
There's gonna be
Wow.
A lot, like, tell me when to stop.
right there.
Right there, okay. How much potential gravitation energy is
Like half that.
it? Like a little less than that?
Oh, half of it.
Half of it. So like this?
Well, at
I
the
would say
bottom,
maybe less than nine.
wouldn't there be more because it isn't pushing up because the spring energy would make it go up?
Okay, so, well, let's, how about if we do this? Well, since we have some discussion, let's go back here. And let's look at this and say, okay, how do we calculate these? How do we determine these? How do you determine the gravitational potential energy?
Oh, isn't it just like the acceleration?
What do you mean, just like the
The
acceleration?
acceleration times the mass, maybe?
Okay, so it's mass, you're saying mass times acceleration, the acceleration of what?
Gravity. Well, yeah, for gravity. it would be
Right.
okay.
Okay, times what? Times the height. Isn't this just the weight of the object times the height? That's a force times the distance, isn't it? That's a work. So it's how much work we do, right? That's really what it's related to.
Wait, so energy is just work?
No, be careful, no. What did we say? What did we say? Work what? When I do work, I do what?
You're
doing what with the energy?
Applying energy. You're changing it.
I'm changing it, I'm transferring it from one place to another. Okay? So the work I did is the energy that I put into the spring. And I can determine how much energy I put in the spring by doing another formula. Okay, but let's talk about this one first. So when this flies into the air, right, it's turning what kind of energy into what kind of energy?
It's turning kinetic energy into potential because of
Okay.
that.
So it had the kinetic and it's turning into potential, and as it gets higher and higher, what happens to the potential?
It keeps increasing.
If it goes higher, what happens to the kinetic?
That's
It goes down, right? Until it reaches its maximum potential energy, which is the highest point, and what's its kinetic energy?
Zero.
Zero, because it's not moving anymore, right? Velocity is zero. That make sense? Okay? So when I'm compressed right here, how much gravitational potential energy do I really have?
Almost none.
Because this is our zero level, isn't it? This is where we're starting from, we're calling this zero. Right? So when we go back to our diagram, how much potential energy should I have? I should have zero gravitational potential energy. Right? Okay. How much kinetic energy do I have?
Also zero.
Also zero. How much loss do I have? Zero. How much total?
The same as the screw.
So it should be the same height as the potential, right? Because that's where all the energy is, right? Okay, so how do I, let's go back to the formula, how do I determine, how do I calculate how much energy is stored in that spring?
How much force you apply to it and how far it goes.
Okay, but can I really measure the force? I don't have anything right here to measure the force. If I just take some spring and I compress it, how do I know how much is in there? Either or you say.
Is this the same as the last one?
That is, because it's a stretch or a compression. So what do you say?
Well, the formula sheet says 1/2 kd squared.
Okay, it says 1/2 kd squared. So what is d in this? Distance what?
Where?
No, what distance?
This is the.
Okay. So this is let's make it easy. I'll put the plate on it. If I started up here and I smash it to here, this would be the distance. It's the distance that I compress, or the distance I what? Stretch it. Because springs, depending on the spring, we can do both, right? We can stretch it to store energy, or we can compress it to store energy, right? Okay? So it is the distance that I compress it, squared, times, what is K?
It says K is F over U.
K is, so you're saying to calculate K, it's force over a distance. Notice the D is different. I wrote it different. We want to do that.
Oh, it's the same.
So it's like we don't-
It'll probably be the same in there, but it represents a different distance. So that's why I wrote it up here. Different. Okay, it's what?
It's like the opposite of work, so work is equal to force times.
Well, I don't know. Is that really opposite?
Not exactly.
Okay. So what's it represent?
The distance it travels.
What else? Think about this. If I have a spring, how much I compress it, that makes sense. That would tell me if I compress it more, I have more energy, right? What else will determine how much energy I can put into a spring?
Yeah, how much
The
it
force you
stretches
have
out.
for like.
Okay, but that's still a distance, right?
The size of this.
Are we not trying to find distance?
Well, no, we already have distance. We're trying to come up with what K really means. What's the other thing that would determine how much energy is stored in this spring?
Really fast.
Property
What?
of the material.
Not fast. yeah, like-
So if I do it faster, it stores more, as opposed to stretching the same distance slower? Okay. How much force? What would determine how much force I use?
That's what we're trying to figure out.
No, what about the spring would determine how much force I use?
Oh,
How
period,
long?
right? How long the spring?
Just how long it is? So a longer spring takes more force to stretch?
Well, if you have a shorter spring,
The
it's more
length- maybe
force
the
to
length
stretch it
between
to
the
same
coils?
distance.
So, wait now, say that again, Eli.
If you have a short spring, a long spring, it takes more force to stretch the short spring.
Are you
to the same
sure?
distance. Yeah,
How are you sure?
because when you take a long spring and you try and pull it, it goes farther than like a short spring, you have to pull really hard. to get it to stretch.
Is that what this says? Is the length of the spring anywhere in there?
No.
No. Okay, so be careful, but I think we're on the right track, because there's some other property of springs, that's the K, that helps us determine how much energy it stores. What's the other property of springs?
The thickness of the board.
What do you mean the thickness? What does that have to do with?
I think maybe the thicker it is.
Diameter?
Say that again?
The thicker it is, it's harder to stretch.
The thicker it is, the harder to stretch. So it's really not the thickness, it's the what?
Diameter.
It's how hard it is to stretch, isn't it? Because I can change that not just by the thickness of the spring, but can't I change the material and do that?
Yeah.
I can change the material and make it harder, right?
So you look at both the distance and the force you use to compress it.
Now be careful, it's not the force, we call it the spring constant. Because it's the force applied to stretch it or compress it a certain distance. That's what this is telling us. It's telling us, in very technical terms, how squishy the spring is. Is it easy to squish, or is it hard to squish? Has anybody ever worked with car springs?
Oh, no.
What do you mean, oh no?
Well, it's like I don't like looking at car springs because if you've ever been like an auto shop, sometimes they have those like big things they use to take the lug nut out of the top. And sometimes like when the machine fails, like the spring like just shoots up and like shoots the lug nut up into the.
Why?
You ever
Because
seen
it
a
has a lot of
trampoline
power.
fail?
Because it has a lot of, not power,
That's pretty powerful.
has a lot of energy, because how hard is it to compress that spring on a car?
Probably really hard.
Very hard. If you put this on a car, what would happen to it?
Probably.
It'd just go flat, wouldn't it? So we have a spring that requires a lot of force to smash it or to stretch it on a car. Because that's the whole point of it. That spring is supposed to help absorb that shock, supposed to keep it from bottoming out. When we put a lot of weight in it, it's supposed to support it. So it has to be a very, very tight or very, very high spring constant, high K, spring. So that spring constant helps us determine how much energy we store. If I have a very tight spring and I compress it a little distance, it can store a whole lot of energy because it's so hard to compress. Does that make sense? Okay, that's what we're saying. This is not a very high K. That's why I can compress it with my little arms
I never said that.
He didn't even, I know he didn't, that's okay. Okay, but we can store at least enough to get that tape into the air and have fun with it, kinda. Okay, so that's our formula for our spring pump, or our spring potential. What was that?
How do you calculate it?
K times d squared times what half.
No, how do you calculate K? Is it gonna just?
The force applied over the distance. So if let's just make this up. If I had a force sensor and I hooked it here and I stretched it, and I stretched it 2 centimeters, and it took 10 newtons to pull that, it'd be 10 newtons over 2 centimeters or 0.02 meters. That's it. Yep. Or if I could take, let's put it on here, if I could take it like stack weights on top of it, if I put weights on top of it, smashed it down, I can figure out how much force I had and how much distance it moved. That makes sense? That's it. So it's really not too terribly hard to determine K. Okay? What's our kinetic energy formula?
It says kinetic energy is half of mass times v squared.
1/2 mv squared. There you go. Some of you have probably seen that before. That's one we use fairly often. We usually start with it in some grade school. Please be careful. That's a popular mistake. To leave off the squares, forget about the squares, whatever. So for instance, a popular question is something like this if we're talking about kinetic energy. If I double the mass or double the velocity, what happens to the kinetic energy? So if I double the mass, what happens to the kinetic energy? It doubles, right? If I double the velocity, what happens to the kinetic energy? It's 4 times as large, right? Because of the square. So be careful when we're talking about that you look at and do not forget that square. Okay? So let's go back to our diagram. So here's our before state, right? Where the spring is smashed down. We have all this total energy that is all spring energy. We release it. We want it to be when the tape is as high in the air as we can get. So tell me, what is the spring potential energy at that point?
None.
Okay, none there. How about the gravitational potential energy? And we're going to do this really just of the tape for these two. Because other stuff, we're going to count as lost, right? So what's the gravitational potential energy?
It's almost max.
Almost max? So like that, if we said, let's draw a little dotted line here, like that,
Maybe a little less.
maybe a little less. Let's go a little less.
Yeah, less. Well, because you're putting energy in place.
So like right there, should I go a little higher?
That's fine.
That's fine, okay?
Gravitational potential.
So what's the kinetic energy up there?
0.
0, right? Okay? And what's the loss?
That's the energy we put into the plate.
So how long of a line do I draw?
The rest of the potential gravitational.
The rest, so you're saying this
Right.
missing
Yes.
should be the loss?
Yeah.
Does that make sense? And the total
Max.
should be the same as what we started with, right? Because we can't just get rid of it. It has to go to one of these.
Why is the energy of gravity a little less?
Well, didn't we have some losses? We had this flying in the air and this flying in the air. We had some scraping going on. So all of the energy from the spring didn't go into the tape, right? Does that make sense? Okay. So we had a little bit of loss, but that loss is right here. So these two together, this one and this one, has to equal that total line, doesn't it? Does that make sense? Okay, let's try something else then. Let's get a different color. Let's go with red. And let's draw it now. Let's do the ending state, our second one, as if just when everything is leaving each other. Just as it comes up. So it's really not pushing on each other anymore. Does that make sense? Okay, so tell me about the spring potential energy just as everything's starting to fly into the air.
Still 0.
Still 0. How about the gravitational potential energy?
Very little.
Very little, so like that?
Yeah.
Okay. How about the kinetic energy?
Got a lot of kinetic energy.
A lot. Tell me when to stop.
Shouldn't it be all?
Stop right there.
No.
A little lower than that.
A little lower than that?
No, higher.
Higher.
Always
Oh.
higher. It should be close to the top.
So close to the top? Is that where we're going?
Wait, is this when
No,
the
not
tape
at
said
the
it's
top.
Apex?
No, this is when the tape and everything is just, we're just
It's
separated.
barely out. So
We
it's
just
like-
barely came out,
So
right?
kinetic energy is really high.
Yeah, it's like almost to the
So
top.
it should be almost to the top?
Yeah.
How about lost?
No.
It's still the same energy that we're putting into the plate.
Have we lost anything yet? Was there any scraping or
No.
anything?
Yeah.
Barely.
There probably was a little bit, so maybe just a little bit again, right?
Well, no.
And the
because-
total should be the same, right?
Wait, but the lost energy is still the same because it's shot into the plate. I mean, there will be less scraping, but
But have we lost everything yet?
no. So
So you're saying, but you're saying, you're saying it should still be up here,
No, I'm
right?
saying it should be.
Because we've already gotten rid of it.
Yeah, you got. It should be higher than it is now, but not all the way up.
Okay, so, well, let's look at it for a second. So when I get here with the tape, right, I've transferred kinetic energy into this. Nothing else is touching it. It's gonna go up and that kinetic energy is gonna change into what? Potential energy, right? Is it gonna gain any other energy from anything that it flies in? So how big should this kinetic energy be? As big as?
Gravity, because it's still going up.
That's what I was.
Well, not low. Same height as this one, shouldn't it?
Why?
Because doesn't it have, right when it's leaving, it has all the energy it's gonna get to make it go high into the air.
Oh, yeah.
Does that make sense?
It'll be-
We don't add anything more that's gonna make it go higher. Whatever potential it has up here had to come from this point right here just as it leaves, doesn't it? It's already lost everything it's gonna lose. Now, these may be scraping and they may not go high, but we're counting all that as a loss, aren't we? We're not separating that one out. So it's already got all the kinetic energy it's going to ever get, which means it's going to have all that turned into potential. Because how much is the tape really gonna lose? What's air gonna do to the tape flying a meter?
Not much.
Not much. We're not gonna count that. So really,
Lost.
this loss should be probably, there we go, to right about there. Because we've got a little bit of this gravitational potential that's gonna kind of turn around and maybe be lost, right? So these three lines should add up to be
Total.
the total of it, right? Making sense? We're just transferring it back and forth, that's all it's doing. Okay? And we can use our formulas to actually determine how much energy each one of those has at different places. So we could say, for instance, with our formula, we could say MGH, we could do this at the top for the tape, equals 1/2 mv squared at the bottom for the tape, couldn't we? Isn't that what we just did in our diagram? We said that, where are we going? I think I erased it. That kinetic energy and that potential are the same, aren't they? And this potential is at the top when the tape's got as far up as we can. And this is at the bottom or just when it's leaving the plate.
Well, so they're
Right.
gonna, so they're gonna have like the potential gravity plus the kinetic energy is gonna be 1.
Well, no,
Well, it's
because,
gonna equal the total.
no, these are gonna equal each other.
But like if at any point they're gonna be,
So at any point when I add all these up, it's going to equal the total, right?
but
So when I,
at
let's
any
put,
point,
so when I add potential spring plus potential gravity plus, whoops, let's write kinetic, plus the loss, that's going to be the total, right?
it's
That's
the,
what
they're gonna equal. The kinetic and potential will equal the maximum kinetic and potential at any
Yeah.
because it's gonna, like, if you were to look at a graph while it was happening, they'd like just change and then go back.
Okay, say that again, let's make sure I want to understand. Say that one more time.
So if you go to the graph,
Right, the graph,
it's gonna, the potential of gravity and the kinetic energy are gonna equal the dotted red line at, if they're added together at any time.
Maybe. Because what we're saying is that it's gotta be a time where those losses don't change, right? So for instance, and that's why I say maybe, if we look at this here, as this goes up, the losses go higher, don't they? Because it's scraping and we're losing some energy. So right here, that's not gonna be strictly true, even though the losses might be very, very small.
Well, once it's in the air.
But once it's, there you go, once it's in the air, absolutely, yes, because then this doesn't ever lose anything more, right? Yep.
But if it doesn't ever lose anything more than
Once it's here.
Yeah.
So if we talk about, if we take a snapshot with our LOA diagram of anywhere along here where it's still being launched, then that's not true. Because losses are still happening, right? It's still scraping. See, I can turn this and you can hear it really scrape, or I can set it there and hardly scrape. So as it's wiggling, losses are changing until the tape leaves the surface. Then the tape has all the energy it's ever going to get. Right? But here, it's still gaining, we're still losing, the losses haven't maxed out. That's what we're saying. Good? You think? Okay, so this is what we're gonna do next time. We're gonna be in a group, and because we got a lot of different things to measure and keep track of, you're gonna be in groups probably of 4, maybe even 5, okay? And we're gonna use this setup to launch it. We're gonna do it like it's a problem, and we're just gonna take some measurements to help you with the calculation. Good?
Yeah.
Okay, let's get to the desk then.